Welcome to an exceptional show for Billion Research's educational series. We're going to learn from one of the greatest living scientists, Professor Frank Wilczek, who won the 2004 Nobel Prize in Physics, has been described by others as possibly the greatest living physicist. Professor, thank you so much for coming on today.
Yeah, happy to be here.
Can you describe to our mainstream viewers, who are used to more simplistic things, how you won this Nobel Prize? It's such an awe-inspiring and amazing feat. And for me as an academic, you've been a hero of mine for nearly 2 decades. But for our viewers, please explain what it is you did.
Oh, you're making this hard to live up to, but the subject of the Nobel Prize was figuring out one of the fundamental forces of nature theoretically. In our current understanding, we have 4 fundamental forces: gravity and electromagnetism, which are the classical forces that have been known for a long time and have had beautiful theories for a long time. In the case of gravity, going back to Newton, and then in the 17th century, and then a fantastically beautiful theory by Einstein of general relativity in the early part of the 20th century. In the case of electrodynamics, it all came together in the middle of the 19th century. But then at the beginning of the 20th century, physicists, when they were exploring the subatomic world, discovered that those 2 laws were not enough, that those 2 forces were not enough, that we needed additional forces to explain what was going on inside atomic nuclei. So one kind of force was needed to explain what holds the nuclei together. That's called the strong force. And
before we move any further, Professor, could you just, for our viewers, help explain how Sir Isaac Newton kind of ropes into this as well?
Well, Sir Isaac Newton provided in the 17th century a very elegant mathematical description of gravitation. The famous law, the force equals a constant times the product of the masses involved divided by the radius between them squared. So that was a model for precision, power. It was a universal law that together with his framework, the laws of motion, classical mechanics, made a revolution and in understanding the motion of planets and the motion of tides here on Earth, many other things, and provided a model of what scientific understanding should be. It should be precise, it should be universal, it should be quantifiable. But in particular, it explained one of the basic forces of nature, gravity, which dominates the motion of celestial bodies, and one measure of the power of his achievement is that after his work, it was the predictions were very precise. It was just a matter of how well you could solve the equations, and the observations got more and more precise as time went on, and but that simple law held up for many decades. There seemed to be at one point a tiny discrepancy in the motion of I guess it was Uranus, and so that was a kind of dark matter problem of the time. There was an unexplained deviation. Something was gravitating that shouldn't be, or something was contributing to the celestial motion, which had no apparent source. But this led people to postulate the existence of an additional planet. And because of the they had this law of gravity. They could figure out where the planet would have to be in order to explain this discrepancy. And sure enough, Neptune showed up as a result. So that was a model of what physical law could be. And was,
If
just
anyone
think
wants
about
to,
it. You write down this equation and it describes the cosmos. It's an extraordinary, and in such detail that you can start to worry about tiny deviations from between the predictions and what you observe at the level of a fraction of a degree up in the sky, and that led to the discovery of new planets. In the 19th century, people started to understand electricity and magnetism, which are big forces here on Earth, and that was all ultimately put together in the middle of the 19th century by Maxwell in the so-called Maxwell equations. And as a and again, they're very precise equations. They're more complex than Newton's law of gravity, but very beautiful when you build up the machinery, the intellectual machinery to understand them, and also extremely fruitful. All of modern radio technology and electromagnetic communication comes out of the Maxwell equations, and they're still used in electrical engineering everywhere. Among one aspect of that achievement was that light was understood, visible light, which used to be a thing in itself, not connected to the other parts of physics in a sense, turned out to be a disturbance in electrical and magnetic fields. So light is understood as a disturbance in electricity and magnetism. It was a great unification.
should we get to
Okay,
some,
so
of the
these were
hard questions now, or?
marvelous examples of what you could achieve through theoretical insight and in understanding the world. Excuse me? Yeah.
I said, should we get to some of the some hard questions now? Is that okay?
All right. Yeah. Okay. Yeah. Okay. I thought you were inviting me to give a long digression, but the story is that we wanted to have equations that were worthy of standing beside those those pinnacles of physics describing fundamental forces, also for these new forces, for the strong and weak forces. And to make a long story short, we were able to discover the equations for the strong force.
Well, I guess getting to the hard part, the technical matter of your Nobel Prize. From what I understood, you essentially found out that particles change their interactions as they heat it up. Is that correct, or am I misunderstanding?
Well, that's one aspect of the theory. So it turned out that the key to understand the key that broke open that cracked the description of the strong interaction, that enabled us to find the correct equations. I mean, if you think about it, whereas with electricity and magnetism, you could work with laboratory-sized objects, and in gravity, you could look up at the sky and see. And it's much more difficult to study subatomic processes, and so finding the laws was a very tricky endeavor, and dominated 20th century physics for a long time.
It was 72 or
but
73, your professor, and you came across it?
when we figured it out,
Yeah.
when we finally figured it out. Of course, our discovery was highly leveraged based on what a lot of other people had done in finding aspects of the strong force and trying to infer from very indirect clues what the basic description might be. But the phenomenon, the experimental phenomenon that turned out to be crucial, is the fact that the basic particles inside protons, the basic particles of the strong interaction, were something called quarks, and they obeyed, or you could infer very funny aspects to the force that between them, that it got weak at high energies or at short distances. And that's something that's very, very difficult to achieve in a way that's consistent with the principles of quantum mechanics and relativity. So what we did was show that when you use that basic fact together with the principles of quantum mechanics and relativity, you were led to a pretty unique proposal for what the equation should be. Then that proposal, those equations were capable of supporting other deductions about experiments that hadn't been done yet, and it works. That's.
Was there ever an aha moment for you?
There were several. I mean, the first thing was that to find a theory that was what did have this peculiar behavior that was built in a way that was consistent with the principles of quantum mechanics and relativity. So what's called a quantum field theory that had this peculiar kind of force law that the forces get weaker at short distances. Most forces get stronger at short distances. And so that, the force of a rubber band weakens at short distances, but a rubber band is not made out of quantum fields. Finding quantum fields that to have that kind of behavior was very, very difficult, and led us to a very unique proposal for what the equation should be. That turns out to be right. So we were.
I mean, would you say that you had, Einstein said he came up with 999 ways to not make a light bulb. Would you say that applied to your work or not really?
Well, there were an infinite number of ways of not doing it. There's only one way to do it. That I guess that was the gift from heaven. That it's very, very unusual. I mean, this apparently kind of arcane experimental fact that really was deduced from a very indirect clues, cracked open the whole problem. I mean, it's kind of a miracle that from that one clue you could figure out everything if you thought about it hard.
It's funny you mentioned miracle and heaven. I went to Amherst College where we had Sir Isaac Newton's desk, hence the question earlier. Or something. Amherst College was given that desk in I think 1890 by an alumnus, and it was brought over from England. And so I was always a big fan. But Newton felt that there was a God because the laws of physics were so beautiful and intricate. We don't talk about politics, sex, religion on the show, but it's just something interesting to note is that Newton did feel that because the laws were so specifically intricate out there must have been someone who created those laws.
Well, Newton was religious, independent of science, I would say.
Really?
He spent a lot of his life, in fact, in biblical studies, probably as much in biblical studies as he did in science. But he didn't see a conflict between those. He thought that by studying the physical world, he was uncovering God's plan in a very literal way. So he was a great and honest scientist. He didn't. So he took the world as it came, but he had full confidence, full faith that that would be a revelation of how God worked. He was very much a student of the Bible and a student of theology and a very much a believing Christian. Yeah.
So where is now the border between math and physics, given that string theory offers a huge number of possible universes instead of just one?
Okay, so I think what you're alluding to there is that fundamental physics, the quest for unification of the four force laws that we know, and in particular, a way of reconciling the basic principles of general relativity, our theory of gravity, with quantum mechanics has proved to be very difficult. It's proved to be very the the uh, the most promising full proposal, I would say, but it's still got a lot of problems, is called string theory.
Mm.
And so we don't really even have a proper definition of string theory, I would say, and we don't have the tools to draw out its empirical consequences in a convincing way. But what seems to be emerging is that the equations and understanding as we have them allow many solutions that correspond to different possible realizations of the fundamental laws, the truly fundamental laws at the level of practically fundamental laws. So, or maybe a more picturesque way to say this is that's often discussed is called the multiverse. It's the idea that although the underlying equations are in common, very different, very distant parts of the universe might have extremely different physical behavior. So that, for instance, the number of spatial dimensions, the number of large spatial dimensions that you could move around in might be different in different regions far away. Might, instead of being 3 as it is in our neighborhood, might be 4 or 5 or 2 or 1.
The possibility of different universes, yeah.
Very different universes. There might be universes in which there's no electromagnetic force, or distant parts of the universe in which there's much different amounts of dark matter. But so very different behaviors, and that leads to the question: well, if there are all these possibilities, how do we predict, or how don't we lose the power to predict what the form of the laws is in effect? One of the grand goal of unification was to explain why we have the forces we do and no other ones, and why we have the dimension, to really get an enhancement of our existing understanding, rather than kind of saying, well, a lot of it is just random and accidental, and it's different elsewhere, and you'll never figure it out because you can't. So the richness, so that's a kind of disturbing situation that I hope is temporary. That there's a kind of mismatch between the theoretical development, which is very rich in mathematics and mathematical potential, and has proved very entertaining to a lot of professional mathematicians who use the methods that physicists are developing to try to understand this theory. So that's great, but on the other hand,
will spatial exploration offer the future for theoretical physics then? Is that, I guess, something you're saying? Or
what's that?
Will spatial exploration, exploration in space offer the future of theoretical physics?
It seems like a long shot, because well, it's certainly not in the sense of space exploration by humans. I mean, space exploration by telescopes and astronomical observations so far have not revealed this potential behavior that distant regions could behave very differently. In fact, quite the contrary. It's a really profound aspect of what we know about the universe, or the part that we've surveyed, is that—
Do you have a view in the beginning, or
the same laws hold everywhere? The same laws seem to hold everywhere, and very precisely.
do you have a view in the beginning, in the Big Bang, or?
Well, the Big Bang is very firmly established. So something that, so very early in its history, I think there are many compelling lines of argument and pieces of evidence that the universe, which is much denser, much hotter, much more uniform, actually kind of a featureless, hot, uniform gas that expanded going towards us, and parts of it collapsed gravitationally into galaxies and planets and stars and so forth. But the beginning was very hot, dense, and uniform. That's what we call the Big Bang. And we can trace that, I think, convincingly using the equations we have down to small fractions of a second past a time when the equations break down. So if we keep extrapolating all the way back to determine kind of a zero of time, when everything was not only very dense but infinitely dense, then the equations break down. So, but if we start from extremely dense and just run it a small fraction of a second, then they work and give convincing consequences. And so, and our understanding of QCD and asymptotic freedom played a big role in that, because the fact that the strong interaction turns off at high energies was what enabled us to understand what the very earliest moments might be like. But when we go back to, if you're asking at the very beginning, then we don't know. Our equations break down. So one of the hopes for a unified theory also that brings in gravity is that we can get a convincing description that is,
well, Professor,
complete, that doesn't have this breakdown of the equations at the very beginning.
Well, just speaking to you as a student, philosophically, if time is constant, isn't there really no beginning then? Isn't the idea of a beginning in itself, in essence, just wrong?
Well, I don't think it's logically inconsistent to imagine that the physical world was so different or earlier in its history that past a certain point that it's not useful to talk about what was happening then, or so there was a singular moment in the history of the universe after which we can understand it in the kind of terms we use to discuss events today. In many ways, to me, but the question is a very interesting one. This goes back, I think, some of the wisest things about this were said by St. Augustine. He was asked by a parishioner, what was God doing before he created the universe? And Augustine's first answer that he said occurred to him was that he was preparing hell for people who ask questions like that. but the question gnawed at him, and he wanted to give a proper answer because it was a profound question. And he gave, I think, a very profound which I think in some form will probably be the answer to this question that gets established by science, which is that he got into a profound, deep meditation on the nature of time, which is in book 11 of his Confessions. And although he certainly didn't put it this way, I think it's fair. I think a fair summary of his conclusion of the argument is that he decided that after thinking about it very hard and looking at what people actually mean by when they talk about time, he said, time is what clocks measure. Time is
time is a made-up idea.
Yeah, time is a construct, is an abstraction from behavior that we see in clocks, but also in other things. Everything that changes changes in the same directions, or changes according to a universal quantity, a universal flow that we call time. And that's where we can dance together, we can sing together, we can agree on what time is in practice. But he said that there has to be something to measure time. Time does not exist as an abstract thing outside of its embodiment in physical objects. So his answer then to the question of what was happening before God created the universe was that since there was no clocks, there were no clocks then, and nothing to measure time, there was no time. And so asking about what happened before that, although it seems to be a grammatically sensible question, actually does not correspond to a physically a meaningful question. Okay, it's kind of, it's the words are misleading. So I think that's going to be the ultimate explanation of what, but I might be wrong. There might be some, it might all, I mean, there are other ideas about cyclic universes that the equations break down, the universe collapses, things get very dense, the equations break down, we can't really predict what happens, but what happens is that it bounces and makes an expanding universe, which is and that's the phase we're living in now. So there are certainly different speculations, but we don't know, we can't decide between these speculations at present.
So reverting back to your work, did string theory or QCD succeed in explaining the quark confinement?
Well, QCD certainly did. QCD is, we can program it precisely on a computer and work out the consequences of the equations of QCD. They're very precise equations, vastly more complicated, vastly, I think it's fair to say, vastly more complicated than Newton's law of gravity, which we just mentioned earlier, but similar in spirit, in their precision. And you can tell a computer precisely what to do to calculate their consequences. And modern computers can solve them in a number of, can do a pretty good job of solving them to answer questions like, do quarks exist as free particles? And the answer is no, that the equations of QCD give you exactly the particles that we observe, no more and no less. So QCD solves the problem. String theory initially was, before it became a theory of quantum gravity, or potentially a theory of everything, as people advertise, was originally invented to be a theory about about strongly interacting particles. And it sort of has built in as an assumption when the confinement of quarks, because it's built out of ingredients that don't include quarks. But that approach to understanding the strong interaction really never worked. Now there are sort of attempts to understand QCD using the tools of string theory, and they've had some modest success.
Do these tools are analytical methods? Is there any future for analytical methods, or is it all simulation at this point?
Well, I mean, there's a future in the sense that people will have fun doing it, and maybe something useful will come out. I think the prospect of replacing the computer calculations with fully analytic calculation, analytic meaning things that people can sit down and write out by hand, one or a few people, like medieval monks doing the calculations by hand. It's logically conceivable, but I would bet large amounts of money against it in the foreseeable future. What I think could very well happen, and probably will happen, and will be a great thing, is a kind of partnership between computers and humans to build on the strengths of each, to combine heavy-duty calculations with approximation schemes that so that the computer doesn't have to start from scratch, so to speak, but can use intermediate models like people use in chemistry. In chemistry, people never use quarks. They use intermediate models, and I think there's a future in understanding nuclear physics at that level, which will be based on the equations of QCD, but will use intermediate concepts, and the concepts will be invented by humans, but implemented in computer programs, and there'll be a kind of partnership. I think that's the way science is developing in many areas these days. I think the partnership between man and machine is the future of a lot of areas of science.
Well, speaking about the future, your book here was just, I absolutely just loved reading it. And I really want all of our viewers to
I loved writing it, I have to say. Yes.
I mean, it was so much fun. It was such an exciting read. And, you know, we're going to have a link to buy the book on our website, of course, as well. But I've got to tell you, I speak to so many authors all the time, but this, I just had so much fun with your book. I couldn't believe, I was so excited to talk to you after reading this, how well you'd done writing this. So I just,
I don't know what to say. Yes, but I just to say that I really enjoyed writing it. It was really, to me, when I first made the proposal, and I thought of it as a chore that I was I wanted to convey things to the public and answer my friends' questions about what I do and how we understand the world now. But as I wrote it, it was really a joy, because I revisited the kinds of questions that I had as a teenager that kind of got me interested in science in the first place. I really came at it from philosophy, really, and even religion. And I ceased to believe in the dogmas that I was exposed to, but it kind of left a hole. I mean, what does it all mean? What are the secret what is the message of the physical world?
It's a wonderful intellectual walk, Professor.
And then, I re-engaged with those questions, and it was really a wonderful experience. It was, so I'm glad some of that comes through.
Well, our last question of the day is, what unsolved mystery, what question in science would you like to see solved in your lifetime?
Let me give you, first of all, a personal perspective, and then I'll give sort of a more expansive perspective. First of all, there's a great problem of physics and cosmology, which is what the dark matter is. Astronomers have discovered that there's a lot of stuff in the universe. It's about 5 times as much or 6 times as much as the stuff we understand by mass. But there's an additional component of the mass of the universe that is not made out of the quarks and gluons and photons and electrons and things we've understood very well. And nobody knows what it is, but I think I know what it is. I think it's something called axions. And we're just now developing technologies that are capable of detecting this dark matter if it is axions, and that's certainly a great challenge and opportunity to either prove it's so or prove it's not so. Another area that is dear to my heart, since it comes out of things that I've worked on a lot and pioneered, is the prospect of so-called topological quantum computing. This uses the properties of emergent particles called anyons that can exist inside materials, that have a kind of memory, and this was a proposal that dates back about 40 years, but only in the last few months has been convincingly demonstrated. Now the technology is such that it's plausible that you can build on it towards making actual working quantum computers, and that I'd love to see that happen, and that would open many doors. Then well, there's also time crystals, which I think could lead to more accurate clocks and or more bringing with other applications. These are new states of matter that, again, so-called time crystals, and we don't really know exactly what they're good for, but it's very exciting to see. And so I'd like to see what are the potentials of that. So those are my three babies now that are kind of maturing, and I'd like to. So those are problems that those are frontiers that are personally very exciting to me, but also to many of my colleagues. But then, to me, the greatest problem on the horizon is understanding how mind emerges from matter. I think now our understanding of what matter is good enough. It's really that there's nowhere to hide. If you believe in what Francis Crick called the astonishing hypothesis, which is basically that mind emerges from matter, then now we have to prove it. And the technologies, I think, again, are becoming available to do that. Progress is being made, but I think the greatest work there is still to come. And it's especially exciting and rich and fertile because as we're understanding how our minds work, how human brains work, and part of the same process is understanding how the minds we're creating work. We have these artificial minds that are becoming more and more powerful, more and more general in their intelligence, more human, if you like. And how do we relate to those? How do we understand their minds, which are clearly based in matter because we've designed them from understanding of matter. And then there are going to be new kinds of minds, quantum minds, the new kinds of quantum computers that are really qualitatively different from existing kinds of computers and existing kinds of minds. And what are those going to be like? What is going to be the psychology of
of course.
advanced minds?
How will they weigh various factors?
So how will they even? Well, I mean, a narrow question is how do we make use of them to design better drugs and do chemistry better, and really exploit the full control of nature that in principle we have since we know the equations. But I think more than that, that it's famously difficult for people to understand how quantum mechanics works intuitively. Our minds are not well adapted to that. That's not how neither evolution did not prepare us for it. And when we learn as babies, we construct a very different model of the world. So it's very difficult to visualize the thought processes of things that are really quantum mechanical intelligences. And I think that's, again, work for the future that will be really fascinating to figure out sort of the psychology, if you like, of quantum computers.
Wonderful. Well, this was a fantastic episode. And again, I really urge our viewers to check out your book. I just loved it. And for an academic-minded individual like myself, it's as riveting as The Hunt for Red October. So thank you for sharing your time, Professor. You're a living legend and a hero of mine.
Thank you very much. Okay.
The honor was all mine. Thank you.